Hello, everybody. My name is Kevin White with the L. Robinson Engineering of Ohio, and I'm joined by my co-principal investigator for this particular project, Dr. Sargan with Ohio University. And today we're going to be covering a recent research project conducted by Ohio DOT on the implementation of an updated CMP spreadsheet, shallow cover pipe. And I'll begin by handing the presentation over to Dr. Sargan for the time being. So Dr. Sargan, please.
Yeah, hi. I appreciate you guys to join us, and I hope you benefit from our presentation. What I want to do is to basically don't take that much time because the most interest is on the spreadsheet that people could utilize hopefully very soon. And so what I want to do is to briefly to explain the foundation or the basic principle that we are operating to get that spreadsheet. And since Tom Shanko, that when they're analyzing the pipes, what they do is they take a portion of the pipe from upper portion, or arch. If it's an arch pipe or if it's a circular pipe, they took part of it and they analyze finding the bending, the thrust, and the capacity of the pipe and all those things. But there was no actual data that because the pipe or the if it's a circular or if it's arch, they are closed loop. And so in that case, they just take part of it. And then they put in both end of the that arch, they put some kind of support. That maybe sometimes they put a pin, sometimes they do that fix. So what we did is that for last several decade actually, that we did many projects for ODOT instrumentation of the pipe. And these are for different reasons, for different purpose. The objectives were different. However, we kept always the data for many years. And so we have data over 50 pipes that heavily instrumented and tested. And what we did is we visited those data again. And what we determined and find out that all of them has a one common conclusion. It's come from it. And that is that it is true that the most of activity or the load is carried by the pipe above the spring. So that means that those assumptions that these researchers did in the past 100 or more than 100 years, they were correct, even though they didn't validate it, but it was correct because still we could use that upper portion of the pipe for analysis or for rating. Which is this also that another the purpose I had by explaining this one is to give a more confident the people that they're using the software that we have significantly capacity left in our pipes, even if the bottom of the pipe is completely corroded. There is tremendous amount of load they still can carry because all the majority of the load is carried above the spring. So in that case, this rating that we want to explain, Kevin will explain it, the spreadsheet is very good for, but is keep in mind, is very conservative. It is, you have in the current, the only time you will get in trouble in the pipe, that Kevin probably agree with me for many, we have experience for many years, is that if you have a problem with the backfill material. If you lose the backfill material or something went wrong with your backfill material, pipe is, as long as your backfill materials are stable and strong, you don't have any problem. The pipe could carry a lot of load. So that basically, so what I want to do is to just show you that when I'm talking about the instrumentation of the pipe, what we have done. Could we go to the other slide, Kevin? The next one. So I'll give you a typical pipe that we instrumented. Again, these are ODOT projects, so but the data is available, report on these available. ODOT has the report. Anybody has interested, they could get it. So what we do generally is that we're measuring the deflection of the pipe, We're using a LVDT or potentiometer. And then what we do is that next one, Kevin. And then what we do is that we're putting a strain gauges to look at the bending and the thrust. And if you look at the gauges are lined up on the two depth above the neutral axle, below the neutral axis, because we want to get from your strength of material when you took it as an undergraduate, if you remember, P over A plus minus MC over I equal to sigma, is that we get the stresses from this combination. One thing I want to point out that culvert, when they corrugated or pipe, they are completely different than any other structure that we design in the infrastructure. Why they are different? The reason is because the soil is applying the load, but soil is also providing the resistance. So you could see when the soil goes inside of the corrugation, you get a good amount of lateral support. So in that case, the material that apply the load, the same material also carry the load part of it. That's the thing. And from undergraduate, again, when the first course we teach in the structure or something, always we are taught that the larger moment of inertia, you can carry more load. But in the pipe, that is not, there is a cases that you will have a larger moment of inertia and the pipe will be very weak. Because in pipe, corrugated pipe, the shape is very important. How the soil and the pipe interact, which is soil structure interaction. That's the reason it's a little different, that we cannot go design it just based on background in geotechnical or just as a structure engineer. This is somewhere between because of that, the way that the soil structure and interaction taking place. So in that case, you could see that we get those strain in those locations, and then we multiply it by Young modulus, because most of the time a pipe is in the elastic zone. And in that case, we go there and calculate the bending and the thrust. Go ahead, the next one. So this is and I think it's a Washington County. You could see that there's a part that we put measuring the LVDTs and strain gauges, and you could see that all the wires and thing is running around. So next one. So in that case, what happened? We applied the load generally with a truck, and so in that case, in this case, we have a tandem truck, and then you fill it up with a gravel, and we know the load. We measure the load in each axle, and then we drive it sometimes 5 miles per hour or sometimes very fast. And then at the same time, sometimes what we just do is just park it to look at under static load to get the capacity. The next one. Here's the typical truck that, and you could see that axle spacing and all those kind of stuff. Next one. This is actually our friend from Washington County. He's a county engineer from Washington County, Roger Wright. And he was very kind to us, to give us this pipe to instrument it and monitor, and they provide the truck and they help us a lot. So you could see this pipe is actually built in 1962 in his arch, and you could see span and the rise and those kind of, all the information on this pipe. Go ahead, the next one. So in that case, you could see that the pipe is sitting on the concrete foundation. And then we apply the load and we monitor a different loading condition. Go ahead. Go some more, because these are the pictures. The next ones. So you could see here is the plot that I'm interested. That you could see static load, the thrust is function of that. If you could see that below the spring is not that much excitement, above the spring is the one that you get a thrust and you get a movement. And if it's in shallow cover, the dominated force is a bending moment. So that's keep in mind, because when what Kevin will be explaining the spreadsheet, he will discuss the uh, interaction between the bending moment and the thrust. And in that many cases in shallow cover, the moment is dominated. But unfortunately, that some of the software that using on the rating, they put the thrust as a dominated. No, but actually the bending moment is a major impact. Go the next. So what we did is we said, okay, if that is a case, somebody always could question that this conclusion that it is right or wrong. So there's a debate that is your instrumentation is good, or you're right or wrong. So they will ask questions. So what we did is that we took the same pipe and we analyzed it with a three-dimensional finite element. Again, I'm not recommending anybody that every day use a three-dimensional finite element. But when we do a finite element three-dimensional is to get inside information for the researcher that we could translate it and give that information to the practicing engineer. But personally, I would never recommend to go use a 3D for everyday use because it's too expensive, too complex. But anyway, we did it with finite element to see what the finite element tell us. Go ahead, next. You could see that first the experimental and the finite element was matching very close. And then the second thing is there's the same phenomena for each loading condition. Is just that spring, above spring is the excitement. Go the next. Okay, so again, another thing, principle I want to explain before I hand it to Kevin is that one of the things is that we use is a plastic hinge in the culvert to see that how much capacity it has for the rating. So to do that, what I want to do is to explain some basic thing that you guys, I know all the engineers that they have background in this and they took this course as an undergraduate when they took a strength of material, but they didn't go that much detail unless they in plasticity unless they take the course in plastic design. So let's go next. So what happening is that the bending moment plastic analysis, you will have a bending moment and the thrust. And so you could see this equation is that it shows that how you calculate the bending moment and how you calculate the thrust. So you can have a pipe that apply load with a truck, you get a bending moment. And then you get a thrust from this equation, but then you also get it from the section. So sometimes we even call, when the plastics, we don't call it sometimes plastic moment capacity, we just say section because they become almost like a section. Next one. Okay, to explain those equations, let's look at the stress strain curve. If you look at the stress strain curve, that when steel goes up to point A as a linear elastic, then from A to B it goes plastic. In that zone of AB, you can experience significant amount of strain or stress strain you could experience without failure. So that is very important. Let's go next. So linear elastic is the first picture from left. The second is that when you load it a little bit more, you go to plastic zone. Then when it goes completely plastic, then you have this shape that is the strain and the stresses just look like those rectangle. Go ahead. So you will have a two-part on that one. One is the bending that it caused the stresses, which is the bottom figure of the three, the bottom one. Due to the M, you get it? Due to thrust, you get that other one. The combination will give you the top one, the figure. So those are basically the stresses that you get for that MMP. Okay, the next. So what's happening is that when you there's an interaction based on those equations, interaction between the plastic moment and the thrust. And so what's happening is that if you, in most cases, the thrust is not very large in shallow cover. If the thrust is less, 15% or less, then the cross-section capacity or the yield stresses, you just ignore it. You don't have to even include the thrust. But if it's above that, then the moment and thrust has to be put together, lumped together. And so those equations that I showed you, that's those equations that they could interaction between the plastic, the moment MP and the thrust. So if the thrust is very small, you ignore it. But if it's not, then you have to take the interaction between them. And that's the one that Kevin will explain. And so I think the model that he will be using it, one of the things is that like they put an MP on at a quarter of the arch and they calculated plastic moment. So if somebody is interested to how you get these plastic moment, if you look at the structure, it's indeterminate because you have support, both supports are fixed. So how you make it determinant? Because if you you form a plastic hinge in both support, and then you have a plastic hinge in MP under the load. Now the structure is determined structure. You could solve it and get those value of MP. So it's straightforward. It's not that complicated. So in many cases, if the load is distributed and you have several load, then you do a trial and error until you find the MP that will be the maximum moment that the arch will experience. So I think that's basically the basic information you need for the stuff that Kevin will explain. And I thank you, Kevin. Go ahead and jump and talk about your spreadsheet.
Very good. Thank you, Dr. Sargan. Next, what we're going to talk about is really Sargan gave us the fundamentals of how we ended up looking at this particular project, because ODOT came to us and the issue at hand is that, as you're aware, Federal Highway is wanting all of the load ratings to be in the BRR software. And that leads to some really difficult situations when we're talking about corrugated metal pipe, especially shallow cover metal pipe. And so ODOT came to us and they said, is there a way that we can utilize BRR for shallow cover culverts? And if not, what can we do to the spreadsheet to bring it up to date and get it to be a little bit more realistic? And so that was kind of our charge for this particular project. So the question becomes, what's going on with AASHTO? And currently what's happening is AASHTO design, Section 12, and for that matter, the MBE, are both based on white and layer ring compression theory. And what that means that our bending moments are minimized. And in fact, the theory says that there are no bending moments at all. And everything is thrust. Well, for shallow burials, that's just not true. For deep, that is relatively true. But for shallow, it's not true at all. And as Dr. Sargan talked about, actually the moment actually starts to dominate the response much more than what thrust does. So if we can get to a point where we can calculate the bending moment, we now, as Dr. Sargan talked about, have to consider the combined effects of moment and thrust. So under shallow cover, bending moments control the performance, which is shown here. We have a load wedge and a live load acting through the culvert, which is there's not enough resistance from the restraint wedge soil, which is on the right-hand side, to resist the loading, which results in bending in the structure. So there's lots of different ways you can go about determining this bending moment. Watkins and Anderson have a method, which I show. Duncan and Drosky have a method. And as Dr. Sargan showed earlier, you can go through advanced three-dimensional finite element analysis, which is certainly beyond the normal analysis methods that practicing engineers would utilize. we focused on Duncan Drosky as the moment that we were going to moment method we were going to utilize. The reason is because it's already in BRR. BRR has this. Michigan DOT added this a few years back as a feature. Now, all that happens is the program calculates the moment based on Duncan and Drosky method. It doesn't really do anything with that calculation. It doesn't provide any sort of a load rating. It doesn't really tell you anything about the combined interactions. So it's important that we understand that, but that's why we ended up with Duncan and Drosky. So what Duncan and Drosky does is it determines what is the moment at the quarter point of the top arch. And that is, in most cases, the critical location for moment. Not always, but it's mostly at that location. So that's the way that Duncan and Drosky went about it. And as we talked about earlier, and these are things that Dr. Sargan talked about the combined effects of moment and thrust, and the same figures that you sort of see that he went through, I show here. But what we end up with is the ways to consider these effects together is what AASHTO has. Is AASHTO has a hyperbolic equation, which is the thrust over the thrust capacity squared plus the moment over the moment capacity, and you add those together, and they have to be less than 1. The Guide to Stability Design for Criteria for Metal Structures, which is a document that comes out very, very often and is updated quite frequently. And you see that equation is very similar in that it looks at the thrust over the thrust capacity plus the moment over the moment capacity. So one is linear, one is hyperbolic. There's other ones that are actually elliptical, where the thrust is squared and the moment is squared. And really it's just a curve fitting. Which way does the particular author want to fit to the data that's available on the combined interactions? So it isn't necessarily a theoretical investigation. It's very much a empirical investigation to get what relationship you want. But since AASHTO already has this equation for deep corrugated metal structure, we felt this was a good equation to go with. But they all use the same thing, which is axial demand over axial resistance plus the bending demand plus over the bending resistance have to be less than or equal to 1. So within BRR, the idea was, is there a way that we can utilize what's available in BRR right now to get a load rating? And so the way that we went about it was we wanted to look at, is there a way to increase the soil cover to get BRR to run, but utilize a change in the density of the backfill material or the load distribution in order to, matter of speaking, trick the program to give us a result that's equivalent to what's actually in the field. So if we went about this, the one thing to realize is that this is a very conservative method, not just because of what Dr. Sargan talked about and the fact that the field results show us that the moments and thrusts that we measure in the field are always significantly less than what we end up with when we do these calculations. But in this particular method, the thrust and moment are both taken at maximum locations. And that's not really what happens in the field. The location of maximum thrust is almost never the same as the location of maximum moment. But in this particular method, we do that. And it's a conservative, it's basically saying this is a conservative way to go about it. So what we looked at, as I talked about, was, is there an equivalency in live load? So is there a way that we can affect the live load portion of the thrust equation to get a similar answer? And the short answer is no. And the reason is because the thrust equation is a squared function, whereas Duncan and Drosky is more of a semi-empirical method. And so the relationships between the two are not the same. So whatever factor we utilize on thrust, we would have to use a different factor for moments. Given that fact, the idea was, let's actually change and go back to using a spreadsheet. And if you remember, ODOT had allowed for the use of a spreadsheet for a long, long time. A couple of years ago, they pulled that that spreadsheet down from their website. But well, our intent was to change that spreadsheet to include moment into the overall idea of what we were trying to accomplish. So we began with the ODOT load rating spreadsheet, and we made several enhancements and revisions to bring it up to date with current MBE and current LRFD design standards, and a couple of other things. So we removed the unsupported buckling check, which was something that we had included earlier on. And the idea behind it was just that the buckling check was conservative. And in fact, it was quite over conservative. So the idea was to take it out and actually add the moment capacity using Duncan Drosky. Then we also implemented the combined thrust and moment interaction equations. According to current load rating and LRFD, we also included a pavement reduction factor, and we also included the multiple presence factor, which is a way of saying what's the likelihood of two loaded trucks being next to each other on the structure simultaneously and having their wheel loads interact with one another. So that gives you a basic understanding of what the project was. And so what I'm going to do next is I'm going to talk about an example on the spreadsheet to walk you through the spreadsheet so you can see how the spreadsheet actually works. So what we're going to look at is the arch that Dr. Sargan talked about earlier in Washington County. And it's a half round arch. It's an 18-foot corrugated steel plate arch. It's a half round. It's a 3-gauge plate. And let's, for the sake of this example, let's say that there's a field measured 10% metal loss and that the condition rating of the structure is 7. So with that, I just want to show real quick the references for what we've done. And also I wanted to thank Ohio DOT for sponsoring the project, Dr. Abbas, who is the lead researcher for the particular project, for the support during this particular project. So with that, I'm going to leave the presentation and go to the spreadsheet. So what I've done is I have the same spreadsheet, just split screen, so that way I can get back and forth between the different tables that I'll need. So we'll start with, I'm actually going to make this a little bit bigger so we can see it a little bit better. So we're going to start with just some header information about the structure. I'm not going to go into great detail on that, but with it, we have different pictures throughout it on how to determine radius, how to look at what the different structure types are, different things like that. So it'll be helpful in terms of determining the information needs for this analysis. So in this particular structure, as we discussed, it's a structural plate. It has bolted seams. If you go to your drop-down box, you can see you can do a corrugated metal, spiral, rib metal, or structural plate pipe. In this particular case, again, since it's a structural plate pipe, it has bolted seams, but you could also go to helical pipe with lock seams if you wanted to. In this particular case, we'll use the NCSPA data sheet, and what this is this is a method for determining the performance of a structure that is deflected less than 5%. And what it's telling you is it's going to tell us what is the change in the buckling capacity of the particular structure. So as long as your deflection is less than 5%, this NCSPA data sheet is the way you want to do it. In this case, I'm saying the height of fill is 1 foot. The minimum height of cover, there's a little diagram off to the side here that tells us about what's minimum cover. The second minimum cover is just for informational purposes. So we'll put in the span and we'll put in the rise of 18 feet. In this particular case, since it's a half round, the rise will be 9 foot. These two do not necessarily have to be symmetric the way I've shown them. And it depends on the shape that you measure in the field. It may actually change. And what you do is this actual top radius of 9 feet. In this case, I've used it as being a mostly undeformed structure. But there's methods up here to utilize this measurement right here, M, it's called the sagitta. And by using the sagitta, we can actually tell what is the radius of the arch at any given point. And by doing that, we can actually figure out what is the maximum radius of the structure by just using a straight edge and measuring the distance between that arc and the structure itself. So we'll go back. And we'll call it 3 gauge in this particular case. I've put in the crown deflection at 2%. And as we talked about earlier, we have a metal loss of 10% in the field. Now, what we do is there are a number of tables in the spreadsheet. So I'm going to go to the section property tables, and there are section properties for most different structure types that you may come in contact with. But in this particular case, we're talking about a 6x2 corrugated metal structure, and it's a 3 gauge. So what we do is we go to this particular column, and we get the wall area, the radius of gyration, the moment of inertia, and the plastic moment capacity. And we enter those values into area, radius of gyration, moment of inertia. Make sure that when you're doing this, that our units are correct. We've tried to make sure that all the units in the tables match the units that are required in the spreadsheet, but just to make sure. And then also add the plastic moment capacity. Then we have to give our seam strength, which is the strength of the bolted seam. And it's looking at, as you remember from Dr. Sargan's at undergraduate, what's the shear pull-out strength of that particular bolt in that particular installation. So I believe there, the next plane, yeah, so we go to seam strength, and again, we go to 3 gauge, and we look to seam strength is 132 kips per foot. Next, we go down and we have our soil density at 120 pounds per cubic foot, or 0.12 kips per cubic foot. The load distribution factor is 1.15, and this is the load distribution factor for LRFR, which is the recommended method of utilizing for load rating for corrugated metal culverts. It's actually slightly more conservative than what LFD would be, but what it does is it allows us to minimize the interaction of different wheel groups during during shallow cover conditions. Next, we have all of our load factors. Our load factors come from this table, which directly comes straight from MBE and LRFD publications. Finally, we come down to what we call our multiple presence factor, small m. That small m is, again, from MBE. We take these values and we say that for between 100 and 1,000 ADT, we use an m value of 0.95. If it's less than 100, we use 0.9. And enter our multiple presence, which gives us the multiple presence factor. This is a factor that's used in calculating this particular factor. What's interesting is that, I'm sorry, I have to go back 1 second and just say that multiple presence factor, this is actually the multiple presence factor for a permit load. And for a permit load, it's always 1 according to MBE. So then the next one down, which is the multiple presence factor for all other load cases, we take from this particular chart here. And once we have that, you take the inverse of it, and that gives you your M. So in this case, we have an M of 1.08. Next thing we have to do is we have to look at the secant soil modulus of backfill. And this is used in the Duncan and Drosky method. So if we go to the Duncan and Drosky factor table, what we're looking for is the constrained soil modulus at the quarter point of the structure if there were no cover over top of the structure for this particular instance. So in that particular case, we have a 9-foot radius. So the quarter point would be at 4.5 feet deep. So what we have to do is we go into this particular table and we have to interpolate at 4.5 feet what is the particular value. So this pipe has been in the ground for a very, very long time. So we are going to make the assumption that it was installed according to ODOT specifications, which require this type of a material. And then we're going to say it's 100% of relative compaction because of how long it's been in the ground. So we're going to use the trend feature in Excel to determine this. And we're going to say our known Y values are between 4 and 6. Our known values are 4 and 6. And we want to know what it is at 4.5. And that tells us 172. We can do the exact same thing for 5.5. And why we want to put in 5.5 is because we're now looking at it for the actual height of cover. In that particular case, we have the 1 feet of cover, so we take the 4.5 from the last iteration, and we add the 1 foot of cover to it, which gives us the 5.5. So we change the 4.5 to 5.5, and in that case, we're going to get the 180. So that's how these values come about. Now, the next value is the moment coefficient factor K4. This is part of the Duncan-Drosky method again, and there is a table right next door that tells us what the values are for different axle configurations. And in this case, we have about 1 foot of cover. And so we would look at 1 foot of cover, and we have 4 wheels per axle. And so we would say 5. And so we then put 5, and we put in 5 for each one of the different loads, all the different test loads that we have to look at. Last input that we have are pavement reduction factor, and the pavement reduction factor is a new addition to the MBE. And what pavement reduction factor does is it allows you to take into account the load spread that occurs because of the stiffness of a pavement. So if you have a situation where your load ratings aren't working, this is a way that you could actually help to improve the load spread, which would basically decrease the pressure on the pipe and could potentially get you in a situation where something that didn't work previously may work. The thing you have to realize about it and be careful about it is that when you do this, your load is spreading further, and so your patch is getting bigger. And what happens is now you have the potential for different axles to interact with each other where previously they didn't. So what you have to do is, if you go through this process, you have to calculate what is the new load spread, and you have to figure out what is the new load distribution factor. And up above where we have this 1.15, you'd have to change this to be encompassing of the load distribution through the soil and through the pavement. And so you have to take an average of the two, a weighted average based on the height of cover of each particular layer. So it's possible. It does take a little bit more work, but there is a way to utilize pavement to your benefit. Your condition factor, we come over to this table, which comes directly from the MBE. And in this particular case, we had a rating of 7, which means that we have a condition factor of 1. And then we also have the system factor. And we look again below, and we give you the tables. And in this particular instance, culverts aren't necessarily in here, but we look at it and say that all other girder bridges and redundant stringer subsystems are 1, and culverts are highly redundant. So using a 1 is a reasonable assumption. That is essentially the output or the input for this. And where we end up is with a series of checks. And what we do first is we go through and we say, what are the design dimensions of the structure? What are the design parameters? Let me make that a little bit bigger. It's basically a regurgitation of the information that you just entered on the other page. But we then get into design calculations. And we look at the critical buckling stress. And there's 2 equations for critical buckling stress. It checks the both of them depending on the overall stiffness of the structure. We end up with one of the 2 different equations to utilize, but eventually we'll get to what's the critical buckling stress. We then look at seam strength, and we make sure that the thrust in the wall is less than the seam strength. From that, we basically check, is the yield of the structure greater than the critical buckling. If it's not, we utilize a critical buckling. And then we also look at the seam strength and we make sure that the thrust is less than the factored seam strength. And if it is, then we get the full capacity of the structure, the full thrust capacity. In this case, the thrust capacity becomes 88.4 kips per foot. We then calculate what is the actual thrust in the structure, so the demand essentially. And in this case, we end up with 1 kip per foot. So as I thought, was both me and Dr. Sargan have talked about, the thrust in the pipe resulting from earth load is very trivial when you consider the capacity of the particular structure. Next, we have to look at live load and how does live load impact that. So the first thing we do is we look at the dynamic allowance. And so we add a dynamic allowance to the overall live load and we get our dynamic factor. In this case, the dynamic factor is 1.29. From this, we then go through and we do the load distribution and we take the particular configuration of the tire patch on the particular test vehicle. And for the HL93, we know the values. For all others, it's a calculated value. So what we do is we input those dimensions for the different values. So we put in the load, and from the load, we calculate what is the width of the tire patch and what's the length of the tire patch for everything except for the HL93. The HL93, the values are given in AASHTO. We then go through the process of distributing that load, and we distribute the load through the fill utilizing this methodology where this load spread is 1.15. So depending on your height to cover H, the load spread is 1.15 times that. And so your patch width increases by the width of the tire print times 1.15 times the height to cover. So with that, we then go through and do a number of calculations for determining if there's an interaction between the axles, what the different axle loads are. Is it just a tire that's being considered, or is it an axle that's being considered? And out of all those calculations, we end up with the thrust in the particular structure. And that's the live load plus the impact. But again, if we look at these numbers, and these are all factored, keep in mind, factored values of around 20. We had 1 for the dead load, so we're talking something below 25. And if we remember, the capacity was 80. And so again, we're at very low demand to resistance ratios when we're talking about thrust. Continuing on, this is what's new. Everything that's done before was in the spreadsheet before. What becomes new is we now start looking at the plastic bending moment at the structure quarter point. And this is using the Duncan-Drosky method. There's a number of different factors that are in the Duncan-Drosky method, and they're based on logarithmic relationships. And if you ever want to, you can get the report. It's not easy to get to, but you can get the report if you ever want to see what's going on. But you can also look at the MPE and look at the formulations in BRR, and it'll actually explain to you how this particular procedure works. So the way it works is we figure out what is the earth moment. And from that, we then add the bending moment for live load. And from that, we end up with, again, we look at, is there interaction between the different axles? Is there interaction between the different footprints of the tires? Things like that. And from all of that, we end up with moments. And so we now have moments and we have thrusts. So we can actually do all of our load rating. So we have our general equations for load rating, which everybody is well aware of. We have a new one for bending moment, and the bending moment is ugly, especially when we combine thrust and moment, because it's a hyperbolic function, which means it has to be solved with the quadratic equation, which is what you see here. But we went through the derivation and we end up with these particular equations for A, B, and C inside of the quadratic equation. So if you add all those together in here, it becomes a very, very cumbersome equation to do by hand, but this is what we've done. And we went through this particular equation development inside of Excel. And so we can actually go through operating load rating factors based on the combined facts of both. And so that's what we have here. We have all the different moment thrust interactions, so we can get a load rating factor from that. We then go through and do the exact same thing for inventory load rating, same equations, just different load factors for inventory versus operating. And this is what we get for our inventory rating factor. We get a 1.01 and we get a 0.93 for the tandem. As we're aware, an inventory less than 1 is not ideal, but it also isn't a end of the world. But we do end up with an inventory of 1.01, which means that the particular structure meets. And we then have an overall summary, and this is what we end up with. I think there is something wrong with this equation because it shouldn't be 120. Oh no, yeah, it should be 120. I have to check that and see. But regardless, it gives you an overall BMS entry value at the end of the equations. And that is overall how the spreadsheet works. With that, I'm going to go back to the PowerPoint and just end up with the final slide, which was here, but I don't know. Oh, well, I apologize. I'm just going to show. If I do that, I end up here. Oh, I'll try and get through these and get back to the end slide. The one thing I did want to mention about this is if you look at what we've just gone through, we spent a huge amount of time discussing the response of the culvert itself. We spent very little time talking about the response of the soil. And so that's one area that we think that when we're talking about load rating in particular, that in the future, there really needs to be more emphasis placed on the soil and the soil condition and understanding what is the overall quality of the soil, because the soil plays such a large part in terms of the load carrying capacity of the structure. And right now we are focusing our efforts on just the ring versus a soil structure interaction system where both components are vital to the performance of the system. So that was what I wanted to close with. Dr. Sargan, anything before we wrap up that you'd like to say?
No, I think you explained it very well, and I think as I said before, and I repeat again, is just all the several pipes that the last 30 years collapsed in Ohio. They lost their backfill material, and so the cause wasn't the pipe; it was the backfill material. And so in that case, this is just a thing that we have to. Obviously, it's a challenge how to evaluate the backfill is not that easy compared to evaluate the steel itself. But we have to focus on it. We will find a way to evaluate the more. Again, it's doable, but it's not economical. A current way to evaluate the backfill. If we will find a more economical way to evaluate it, will be the one that to try. Because other than that, currently you could always send a big cone and you push it in the backfill, and that will give you classification of the soil and the density of the soil, and that's all you need. But again, it's just costly. So, and it's not something that the county engineer could go afford to explain that kind of money. So hopefully we'll come with a simple way that evaluate the backfill material.
Very good. With that, we thank you for your time, and we're hopeful that you can derive a benefit from this particular project. So thank you very much.
Thank you, guys.